Okay, good morning, everyone. So today and perhaps Friday, we're going to look at four examples, right? We have covered all the theory. Um, there's only one example problem remaining in AC analysis, and there's two more that I wanted to do in power. So three example problems, but two of them for AC analysis and two of them for power. Because the second problem involves both AC analysis, where we find voltage and current, and power quantities, both. So one example is for both. So let's begin. Now, in the interests of saving time, I already have my annotations written out on the, I can't set up the system. See, section 2, chapter 5, example 5. So examples 1 and 2, we saw how for AC sources, we can represent the sources as a vector quantity using complex numbers, and we represent components as impedances, again, using complex numbers, right? And this is all in the purpose of simplifying the math. So examples 1 and 2 dealt with sources. Examples 3 and 4 dealt with components. Now we'll combine everything together in example 5. In example 5, we have a circuit where you have a source and you're applying it to a resistor, inductor, and capacitor. So the first thing I always strongly recommend students do is to draw the equivalent impedance diagram. Okay, the equivalent impedance diagram, where you represent each component with its complex counterpart. Okay, meaning the source is represented with its phasor, Vs, right? If it's voltage I, then it's Is, or phasor I. So it doesn't really matter whether it's a voltage source or a current source. You represent the source with its complex counterpart, which is the phasor, and then you represent each of the components, the other components, with its impedance. So impedance of a resistor is R itself, so remains R. L becomes ZL, C becomes ZC. And what this does is it reduces that AC analysis to a very familiar circuit, which is from chapter 1 and 2. Actually, chapter 2 specifically, resistive circuit analysis. And from this point on, without thinking about the math, without thinking about anything, you go back to chapter 2 and you see how you can reduce the circuit to one single impedance. You apply the exact same techniques that you learned in chapters 1 and 2. No different. So here, what can we say about these impedances? All of them are in series. So to reduce all of them to one single impedance, simply combine all three of these together. R plus ZL plus ZC gives me the total equivalent impedance as ZEQ. ZEQ. And then the direction for I is already given to us. But if it was not, what could we say? Current for a source goes from low to high, minus to plus. So current would always go in this direction, meaning it's making its way around here. So again, I of t is given to us. I mean, the direction for I of t is given. But if it was not, we should still be able to, again, apply the same techniques we learned in chapter 1 and write it out that way. All right, so let's see what we need to do next. ZEQ is R plus ZL plus ZC. The question being asked of us is to find I of t, VR, VC, and VL. This is very important as to the form of your final answer. If it says as a function of time, means of t, or it is in lowercase, like you see here with VR, VC, and VL, it is asking you for the answer in the time domain. Okay, so all of these should be in the time domain expression, meaning as a function of time, as a function of t. So your final answer has to be cos of omega t. You cannot leave it in phasor form. Phasor form would be an uppercase V or an uppercase I with these marks at either end. So this would be phasor form, and these would be the time domain expression. So if the expression as lowercase quantities, time domain expression, even if the function of time t is not present. So in this case, all four quantities need to be a function of time. These annotations should be at your end on your class notebook, right? And so might want to write down anything else that I'm talking about other than the notations. They're already there. And then, of course, asking us to draw the phasor diagram. So let's begin. We have ZEQ is equal to R plus ZL plus ZC, meaning we need to find ZL and ZC as a first step. In order to do that, I need to look at the expression, which is J omega L. I need omega. So you compare the source with the standard time domain expression, which is V of t. V of t is Vm cos of omega t plus or minus theta. That's the standard expression. When I compare the source with that expression, I can write Vm, or I can extract the value for Vm as 100 volts. Omega is 500 radians per second, and theta is plus 30 degrees. Plus 30 degrees. If the expression was in sine of 500t, you convert it to cosine, subtract minus 90. So sine of 500t plus 30 would become cos of 500t minus 60. Right? So if the expression was in sine, you have to put it in cosine first. Subtract 90 degrees from the phase angle, which is again something that we saw previous examples. So once I have the value for omega, I have the value for Vm and theta, I can write the phase, not phase, sorry, I can write the phasor for Vs. Phasor representation for Vs is the magnitude of 100, phase angle of 30 degrees. Do not forget your units, volts. Right? So far, so good. We have one part of the circuit done. We have taken care of the source. Source is now represented as a complex quantity. That is by far the most easiest and the most straightforward, right? Because you simply take a look at the magnitude and the phase angle, right out the phase. Now, we represent the inductor and the capacitor by its complex counterpart. So we use J omega L for rectangular coordinates and omega L with an angle of 90 for the polar coordinates. And the reason I do both at the same time, again, is because of my hesitancy to upgrade to a newer calculator. I do have a newer programmable calculator, but I think I'm too set in my ways now. So I have the calculator that is from 1992, still works, still runs great, but limited in its abilities, so I need those calculations. Anyway, the point is, again, as I keep repeating, if you have a programmable calculator, you may not need to find both at the same time. It is still good practice to do it, but again, I leave it up to you. So anyway, ZL is J omega L. ZL is also given in polar coordinates with omega L with a phase angle of plus 90. So always going to be plus 90 because the voltage for a inductor is always ahead of the current by 90 degrees. Eli the Iceman, remember? Voltage is always ahead of the current. For a capacitor, voltage is always behind the current by 90 degrees. So always minus 90. Hence minus J and minus 90. That is also an indicator of what kind of load it is, right? That's also an indicator of what kind of load you have. If your load Z is equal to R plus JX, or plus minus JX. If the reactance has a positive value plus J or plus X, that means it is referring to an inductor. If your reactance has a negative value, it is referring to a capacitor. Now, in this circuit, ZEQ is going to be combined, right? R plus ZL plus ZC. So, depending on the value of the inductor and the capacitor, the impedance will cancel each other out. So, inductor impedance is plus J150, capacitor is minus J50. The capacitor is reducing the total impedance of that circuit. It's an important point to remember because it'll come up again as power factor correction when we get to power analysis, right? We have plus J150 minus J50. So the overall impedance is just plus J100. The inductor impedance is offset a little bit by the capacitor impedance, meaning the reactive power for the inductor is going to be reduced because of the capacitor. Okay, this example, we are not doing power, but again, the concept is still valid, right? Everybody sees that? You get 100 plus J100. Now, I'm going to convert it to polar quantity because the next mathematical operation I need to do is division. If you look at the circuit, I have ZEQ, and I need to find, so I have voltage, I have impedance, and I need to find I. What comes to mind? V equals IR, V equals IZ, Ohm's law, right? Ohm's law. So, V equals IR in AC analysis would be V is equal to IZ. Question at the beginning was find the total current being supplied by the source. So I is equal to V divided by Z. I need to perform a division, Vs over ZEQ. Same thing that we have done in chapter 2. Resistive circuit analysis was the first analysis technique that we learned. And those are the techniques that you would use for the most part for AC analysis, right? For EE majors, we do example problems where you would do AC analysis using mesh current, node voltage, Thevenin's, Norton's, all of the good stuff. But I'm guessing you all are not interested in doing that. Now, typically I don't do because there's just not enough time, and I just think it's a bit much. The techniques are what is more important. So, does this make sense? Let's pause for 10 seconds. Let me know if you have any questions. Any questions at all? Good question. Yes, it will always be the same. So the frequency, so when you apply DC, when you apply a voltage or a current, it changes the voltage or the current. When you apply it for AC, you have the voltage or current, you have the phase, and you have the frequency. Well, the inductors and the capacitors and the resistors will only change the magnitude of the voltage and magnitude of the current, and it will change the phase, but it will not affect the frequency. So the only two things we need to find are magnitude and phase. So DC, we only have to find the magnitude. AC, we have to find magnitude and phase. We can ignore frequency. Frequency does not change. It will always, yeah, it'll always be the same frequency. Yep. Yeah. Yep. Any other questions? Any other questions at all? So we perform our division. I is equal to Vs over ZEQ. And we obtain I as magnitude of 0.707 and a phase angle of minus 15. Minus 15. That is the phasor form. You need to perform an inverse phasor transform from here to here. And so magnitude 0.707, cos of the same frequency, 500t, and a phase angle of minus 15. And overall units, amps because it's describing current as a function of time. So your final answer, if the question asks you for phasor of I, you can leave it here. If it asks you for phasor of I, uppercase I, you can leave your answer here at this point, 0.707 with a phase angle -15. But because it asks you for lowercase I, and in this case specifically it's asking you for I of t, I as a function of time, you have to have the answer as cos of 500t. Cos of 500t. Otherwise, well, reduction of 1 or 2 points. Inverse phasor transform, right? Well, after that, it's rather straightforward again. We applied Ohm's law to find the total current I. We apply Ohm's law again, expand the circuit back up again, and you apply Ohm's law to each one of these components right there. So VR, voltage across R, becomes I times R. VL is ZL times I or I times ZL, and VC is I times ZC. So VR is I times R, VL is I times ZL, and VC is I times ZC. Multiplication, multiplication, multiplication. Hence, at the beginning, I found the ZL and ZC values in both rectangular as well as polar coordinates. Okay, rectangular as well as polar coordinates. And you can perform the math on your calculator devices and find the final answer, transform it back into the time domain, and you get values for VR, VL, and VC. All right, questions? Any questions at all? Sure. Yeah, I will talk about that. You're talking about the voltage division? Yeah, that's what I'm going to talk about next. Yeah. So the techniques, again, they remain the same. This is what we learned in chapter 2. So if you want to take a shortcut, then we use voltage division. So again, let's wait for any questions and then I'll talk about that. Any questions at all? Okay. So think back to chapter 2 again. When you apply a current to a parallel circuit of resistors, current gets divided. When you apply voltage to a series connection of components, the voltage gets divided. So you can apply voltage division and find the answers for each one of these voltages, right? Without having to go through the other double application of Ohm's law. So voltage division, of course, states that when you have a voltage applied to a series connection of resistances, a fraction of that source voltage appears across each resistance. So for AC, it works the same way. A fraction of Vs appears across each impedance. So it becomes Vs times R over ZEQ, Vs times ZL over ZEQ, and Vs times ZC over ZEQ. Plug in all of these values. You already have all three of these values. So practice this on your calculator, right? This is going to help you in the final exam to make, faster, speed up your calculations. So hence student practice. Now, in this case, of course, we were asked to find the total current I. So we could not skip that step. Okay. If total current I was not asked, then you can directly apply voltage division. But total current I was asked of us, so we have to, we had to find Vs over ZEQ. Make sense to everyone? Let's see, 10:30. You're doing good on time. Any questions at all? Yes. No. ZEQ is just a vector representation. It's not a function of time. Yeah. ZEQ depends on frequency. It depends on frequency, is 2 pi FL. So ZL is 2 pi FL. Frequency is the inverse of time in that sense. But When we do the phasor representation where we do cos of omega t, not that. It's not time varying that way. It depends on the frequency. All right, let's look at the phasor diagram. So phasor diagram is simply the graphical representation of the vector, right? Graphical representation of the vector. If you're representing both the source as well as the impedance as a vector quantity. The source is the phasor, the components are impedances, but they are both complex quantities. And to describe a complex quantity or to describe a vector, you only need two things. You need the angle it makes with the real axis and the length of that vector. Both of them are not to scale. Okay, both of them are not to scale on this chart, on this diagram. So let's take the source first. Source Vs has a magnitude of, what is the magnitude? 100 with a phase angle of 30. Yeah, 100 with a phase angle of 30. So what you would do is you would draw the real axis, you would draw the imaginary axis, and you would find the phase angle first. Counting counterclockwise from the zero axis or the real axis is a positive phase angle. Going clockwise is the negative phase angle, right? So a plus 30 phase angle is clockwise and somewhere over here. And that's all you need to do. You find the angle, draw a line at that angle, and that is Vs. That's it. That's drawing the phasor diagram. And then VR, VL, and VC, we'll draw VR. VR has an angle of minus 15, so it's going in the clockwise direction. IR, actually IR, IL, and IC are the same current, right? It's a series circuit, so the source current is the same current that is flowing through all the components, and that is noted by the small arrow right here in black. It has the same angle as the voltage for the resistor, which makes sense because voltage for a resistor and current for a resistor are always in phase. If you get a different answer, then you're doing something incorrect. So VR and IR has to have the same phase. In this case, IR is also the source current and the current for the inductor as well as the current for the capacitor. It's a series circuit. Same current I is represented for all four quantities, including the source. That magnitude is very, very small. It's like 0.707. So it's, if I was to actually plot it to scale, it would probably be like a tiny dot. So this is an exaggerated number. Does that make sense? It's minus 15 for both I and VR. Then VL has an angle of plus 75 with the real axis. Minus 15 plus 75 gives you 90 degrees. Voltage for VL is 90 degrees ahead of the current. It's rotating counterclockwise. So anything that is, well, has a positive, larger positive phase angle is ahead of something that is, well, smaller angle. And so VL is 90 degrees ahead of I, which is what it should be. Eli the Iceman again. Voltage for inductor is 90 degrees ahead of the current. Capacitor is 90 degrees behind. So it's minus 105 with respect to the real axis. Minus 105 gives us minus 90 between the current I and VC. And because the inductor and the capacitor share the exact same current, for this case and only this circuit particularly, the phase difference for an inductor and a capacitor voltage is 180 degrees, completely out of phase, inverted. And that is only because they share the exact same current. If they were connected in parallel, or if they were like some other neither series nor parallel, as you will see in the next problem, then it would not be 180, it would be something else because the current would not be the same. Make sense? Right? So the angles could be any value. You got minus 15, plus 30, plus 75, minus 105. But the individual relationships for every component still remains the same. It still remains true. Plus 90 for inductor, minus 90 for capacitor. So that's a big indicator of of how you would verify your answer. All right, questions. Does it all make sense? Does the process make sense? The math might take some some practice, but the process should still be familiar to everyone. So let's take a pause and let me know if you have any questions.
Can you please scroll to the left for a second?
Sure. So right there.
Yeah, thank you.
Again, the annotations should already be available to all students in the class notebook at your end. So the next circuit, while you're thinking about this, is very similar. Again, uses R, L, and C, but you are now asked to find the power for every component. So we'll solve for the voltage and current in the circuit. So that's an example again of AC analysis, and then we'll solve for the power. Any questions about any of this? So again, two ways to solve. You apply Ohm's law twice, or you apply voltage division. Multiple tools in your toolbox. It's up to you on which tools you wish to use. So if there are no more questions, I'm going to call chapter 5 at an end. We'll close the curtains on that and move on to chapter 5.5 AC analysis examples. So chapter 5.5. Let's look at AC analysis. Let's look at the power triangle first. So power triangle is, what is going on? What is the all right, let's see if it works now. Okay, power triangle. Three sides of a right angle triangle. Real axis has the real power P. Imaginary axis has the reactive power Q, which has to do with the reactance, which again is a complex quantity, a part of the complex quantity of impedance, right? And the third side is the magnitude of S, simply given by the product of the voltage and current, the RMS values, magnitude of S. S, of course, represents the total complex power. So from this right angle triangle, from this graphical representation, we can write these equations. P is equal to V RMS IRMS cosine of theta, and Q would be sine theta, right? It's the two sides of a right angle triangle. So P is hypotenuse times cosine of theta, and Q is magnitude of S times sine of theta. Theta is also known as the power angle, and is simply the phase difference between the voltage and the current. Phase difference between the voltage and the current, theta V minus theta I. So it is also the impedance angle. Impedance is V divided by I. So the phase would be subtracted, theta V minus theta I. Now, it is important to remember this applies to a single component. Yes. Yes, V RMS times I RMS here in this. Oh, no, RMS values do not include any angle. RMS values is the average, remember? So the hypotenuse is just showing you the magnitude of the complex power. The power angle is separate. So this is just the magnitude. The power angle is right here. So magnitude of S is, well, it's S is magnitude of S, and the power angle theta does not include any information about the angle. Make sense? Right? So what was I saying? Oh, yeah. P is real power, Q is reactive power. So if you take a pure resistor, does not have any phase difference between the voltage and current. So theta, power angle for a resistor, is always 0. What do we get? P is equal to V times I. That's it, which is what it should be. If you take simply QL and QC, meaning if you wanted to find the reactive power for an inductor, reactive power for a capacitor, what would be the phase angle? Sine of plus 90 and sine of minus 90, right? And you need VRMS and IRMS for that particular component. So this equation, or these equations, these two equations, are more appropriate when you have a source and you're trying to find the answers for a source, directly for a source. Okay? Because a source is going to supply, well, whether it's supplying, whether it's a current source or a voltage source, it will supply voltage and current both, right? But in a circuit, it could have resistors, could have inductors, capacitors, could have everything. So the power angle that is generated for that source would be some random value. For one particular inductor or one particular capacitor, these angles will be fixed, right? So these are better to apply when you're trying to find power for a source, not for individual components. You can still use it for individual components, but you will need the individual voltages and currents. And you will see that in that example problem. So if you're trying to find it for the components, you would use this. You remember from chapter 1, P is equal to I squared times R, P is equal to V squared over R. The exact same equations, except it's AC, so we need the average value, which is described by the RMS values. If you're trying to find the power for a resistor, you find the current or the voltage for the resistor, and you apply these two equations, either one. If you're trying to find it for the capacitor or inductor, you replace the R with an X, which is indicating the reactance. So QL would be I square RMS or I RMS square times XL, or V RMS square over XL. Same thing for a capacitor. I square RMS times XC or V RMS square divided by XC. Same equation, same form. The only thing is we are now talking about reactance. X is the reactance. It is indicated by the imaginary letter J. So ZL is JXL. ZC is 1 over JXC. Okay, minus JXC. So X does not have the imaginary number J. So Q also does not have the imaginary number J. It is when you include Q as part of the equation for S, that's where you will represent the imaginary number J. So S becomes P plus JQ. Q by itself does not have J. QL is always going to be positive. QC is always going to be represented by negative. Okay, negative. Even though power in real life is never positive or negative, in order to balance out mathematical expressions, we'll put QL as positive because impedance angle and power angle for a inductor is positive. Angle for capacitor would be negative. So QC would always be minus. All right, so let's look at Example problem 1 for AC power. We have a source, sinusoidal source given by 10 sine 1000 t. In order to write the phasor form, we would convert that to cosine, and I would get an X phasor for Vs as 10 with an angle of minus 90. And on the other side, I would draw out the equivalent impedance diagram. Right, equivalent impedance diagram. So each component is represented with its complex quantity. Vs of t is represented by the phasor Vs. L is represented by ZL, R with R, and C with ZC. Don't know what is up with the system today. Oh. And then current I is not given to us, but we can write the direction of the current. We can write the direction of the current based on the sign given to us for the voltage source. For a source, current always goes from minus to plus. So it's going up, right? It's going up, makes a right turn, goes through the inductor. So the inductor and the source share the exact same current I. Exact same current I. And then of course it gets to this node. We see R and ZC are in parallel, gets divided, IR and IC. Again, similar, this is similar to a problem that we actually did in chapter 2. And then R and ZC we can see are in parallel. So R parallel ZC. I'm going to call it ZRC. You can call it anything, but indicator is that it's in parallel. So ZRC is the total equivalent impedance of the resistor and the capacitor in parallel. Keep in mind, as a quantity, a resistor and capacitor cannot be combined, but we can indeed combine the impedance of the capacitor with that resistor. Okay, it's important to keep in mind. So resistor and capacitor cannot be combined, but the impedance can be combined. Oh no, what is up with the system? Probably needs like a reboot or something. Anyway, let's just move forward. I can't. Okay, so ZRC is a combination of R and C in parallel, and then we can see ZL is in series with ZRC. So total equivalent impedance, ZEQ, in our case, is ZL plus ZRC. You apply the same techniques, you apply Ohm's law, you find the total current I, and then we can expand it back up to find voltage across the inductor and voltage across the capacitor and the resistor. Now, the original question is find the power for every component. And I'm going to solve this using 3 different methods. Well, not 3 different methods, but 3 different applications or equations. Okay, so let's go to the first one. The first one, omega is 1000 R from the source, so I can find ZL and ZC. Okay, ZL and ZC. I'm finding it for both rectangular coordinates as well as polar coordinates. That's just a habit that I've picked up over the last couple of decades. ZL comes out to be J100, ZC comes out to be minus J100. Okay. Then ZRC, parallel combination of R and ZC, product of the two divided by the sum of the two. And this is why I have to have both polar and rectangular. I need to perform a division. I need both the denominator and the numerator to be in polar coordinates. So I have to convert it back and forth. Obviously, you can jump from this step directly to here if you have a programmable calculator. Again, this is something you need to practice on your own. All right. And that gives me a total impedance of 70.71 minus 45 or 50 minus J50. Once I have ZRC, I add it to the inductor impedance and I find ZEQ. And you can see the same thing again. The inductor impedance has a magnitude of 100, right? J100, but it is offset. It is offset by the capacitor impedance. Okay, capacitor impedance. So J100 minus J50, the overall impedance presented to the source is only plus J50. Make sense to everyone? And this is crucial for this problem because we're trying to find the reactive power for both inductor as well as the capacitor. So impedance for the inductor is plus J100, magnitude of 100, but it is offset by the inductor, the capacitor impedance. Then total I is Vs over Zeq. I find the total current I with a magnitude of 0.1414 and a phase angle of minus 135. Minus 135. Find the voltage across the inductor. You can do that easily by applying Ohm's law. I times ZL. Can apply Ohm's law and find VR or VC. VR or VC. They're both the same. R, if your resistor does not have any phase angle, so you can find VRC just by multiplying it with ZRC. And once you have that, you can find it using voltage division or applying Ohm's law, either ways. If I apply voltage division, again, the same thing, Vs times ZRC over Zeq, and I get magnitude of 10 with a phase angle of minus 180. Once you have that voltage, you can find the individual currents IR and IC. Okay, IR and IC. Now, this is just, I'm showing what the quantities, all quantities that we can find. To find the power, we do not need both I and V. Okay, we don't need both I and V. We just need V or I. We can do V square over X or I square times X. And that is what I show in the next step. On the left side, I use voltage. On the right side, I'm using current. So again, the question was to find the power for every component. In order to find the power, I do not need both voltage and current. That is one advantage of using the other equations, right? If you use VRMS, IRMS times cosine of theta, we need both voltage and current for that component. So that is one disadvantage. But on the left here, I have V square over R. Here I have I square times R. Inductor, it will simply become V square over XL, VC over XC for the capacitor. And here it becomes I square times XL and I square times XC. Right? You take your pick. These are all tools in your toolbox. It is up to you on which tool you wish to use. Equations are the same. I square times R, V square over R. Does that make sense to everyone? You can see that the answers are exactly the same. No change. I left the inductor as a practice for students. It's not going to take you long. The first application is find VL. VL can be found from Ohm's law or voltage division. You can do both, practice and make sure you get the right answer, same answer. And then you plug it in here. In this equation, this should come out to this exact same value, which is 1 VAR. Capacitor VAR is minus, and so it becomes minus 0.5 VAR. S becomes 0.5 plus J0.5. Total reactive power requirement by the inductor is 1, but the capacitor supplies half of it. And so the source only supplies 0.5. This is the total power being supplied by the source. Okay. S is equal to P plus JQ. P is the resistive portion, Q is the inductive and the capacitive portion. Does that make sense? Right? Total requirement of 1 VAR is now being provided, or half of it is being provided by the capacitor. And that is power factor correction, where a capacitor will apply or supply certain voltages to reduce the total power requirement. Does the process make sense? The other equation we can use is this. VRMS, IRMS times cosine theta and sine theta for P and Q. So we can apply to the source. The source voltage is already known to us, minus 90. The source current is what we found as I, which was minus 135. So the overall power angle is 45. And you plug that into the source current and voltage, VRMS, IRMS, and you obtain 0.5 watts, 0.5 VAR. It's the exact same as what we obtained above. No change. 3 steps, the same answer. So if the question was to find only the power only for the source, you could simply find voltage and you jump to this equation right there. You find the current, total current provided by the source, and you can skip all the preceding steps and go over here. One other method, even shorter, is to use this equation. So the third one, the total complex power S for the source, so SS, is half VI asterisk. What does the asterisk stand for? It stands for the complex conjugate of the complex number. Complex conjugate simply is the opposite pole. So A plus JB becomes A minus JB. R with the angle of theta becomes R with the angle of minus theta. Minus theta. So half VI asterisk, this V and I are phasors. Even simpler. So you take the V of t information that is given to us, plug it directly here. 10 cos of omega t minus 90 degrees. So 10 minus 90. Current we found was 0.1414 with a phase angle of minus 135. Complex conjugate would be plus 135. So half VI asterisk. Simply solve this equation and you get your final answer for the total complex power for the source is 0.707 with an angle of 45. You convert it to rectangular coordinates, so polar to rectangular conversion. You get 0.5 plus J0.5. Compare it to the standard expression, and you can get P as 0.5 and Q as plus 0.5. One-step answer, or at least two-step answer. So 3 different methods. The first one, we found the current and we solved for individual components because again, the question required power for every component. Second one, we can find it directly for the source. The third one also, we find it directly for the source. Inductive power requirement is +1. Capacitor supplies half of that. So the total supplied by the source is just plus 0.5. So my angle, instead of being large like this, is much smaller. Make sense? All right. It's a lot of information. So review this video as soon as I post it later today. I'll go to my office and post it right now. There's one more example. I might either I'll decide and solve it either on class on Friday, or I might post a video about it. But we'll pick up here either on the video or on Friday. We'll end class here for today, and I will see you all on Friday. I will be in my office for office hours. If you can make it to in the next hour or so, you can see me over Zoom. Just send me an email, and I'll hop onto Zoom. Okay, just don't wait in the Zoom meeting without letting me know. All right, have a good rest of your day, and I will see you all in a couple of days.